Okay, this is a bit challenging topic. This example 2, assign phi where the number is less than and equal to or equal to 3, otherwise 9. Okay, so we are going to use the logical matrix as a logical indexing. Okay, so here, when you plug in the logical matrix as a logical vector, so logical indexing vector, since a logical matrix implicitly converted to the flattened vector in our linear indexing order. Okay, let's take a look at this example. What is this one? Okay, this one is the relational operator between the matrix and scalar, right? So that's why this one is element-wise operation. True is assigned where the number is larger than 3. False is assigned to the rest. So index LG3 is to become like this. Okay, so I mean that this one is this question is the same with assign 9 when the number known is larger than 3, right? Otherwise 5. Okay, that logic is better. Okay, so num is larger than 3, and then this location is 0, right? So false, and then this rest of the location is the 1. Okay. Okay, can you get this? How we can get this index logical 3 matrix? Right now, this one is a matrix. Okay. What if we can use this matrix as a logical indexing? Okay. And then this matrix implicitly converted to the column vector. So column vector. So this one is actually flattened like a 0, 1, 1, 0, 1, 1, 0, 1, 1, because that is okay. That is the linear indexing order. Okay, so this one and this one is the same. Okay, that's why vector LG3 logical 3 become all like this. Where is the 1 location? 4, 7, 5, 8, 6, 9. Okay, can you get it? Okay, so basically in here, this one is the same with this one. This one is like a flattened vector in a linear indexing order. Okay, so let me show some example how you can write this problem. Okay, the first option that you have to know is the script using the loop and the selection statement. Okay, so let me check this. Okay, then you can get the row size and column size. Okay, column size and then size A, right? And then you make the double loop structure. Column size, okay, and then to here, let's say B is our resulting matrix, right? B is initialized with the size of the A. Okay, how to design this action part? F, this value is the so larger than 3, and then B at the same location is assigned to 9 is assigned to this location, else B become 9 5 and then N. Okay, do you understand this logic? So if you run it at the end, B, you can get the B matrix, this one. Okay, this one. Okay, this is the option 1. Here come. By the way, if you select and then Control R, you can comment it out the multiple line. Okay. Option 2 is the using the operator. Index logical 3 is A, so larger than 3. Okay. We don't need to vector logical 3 to solve this problem. And then we can directly plug in this logical vector to the B matrix. B is your resulting matrix. Okay, let's say B is initialized with this one. Okay. Then B is 0. Okay. But in this case, I initialize with just A because we are replacing the all value. Okay, but this is the better way. Okay, initialize with a B. Then this one become a 9. And then this is the important part. How can you assign the 5 in the rest of the location? Okay, we just used this not operator. This is the key part of this problem. What is the not? Not is 0 become a 1, 1 become a 0. Okay, basically in this question, so you're assigning the 5 on this, 9 is on this location. So if you flip it using the not, because this is a logical matrix, it's not, this become like this. Plug in this logical vector and assign 5, you'll get this one. So B not, okay, you copy this not and then 5. If you run it, B become like this. Make sense? Okay, here's a simple problem. How to assign 8 on the diagonal element. We already solved a similar problem in the previous model. One way is to use a loop structure. We are accessing the diagonal element using this II and assign 8 to the corresponding location. Okay. How to assign the number in the reverse diagonal location? So we can compute this column location based on the row index. For instance, the row index is 1, column is the third, right? Second is the second, third, and first. The summation is arrays of 4, right? So 4 minus II is the column location. So we are using this syntax. Okay. how to solve this problem without the loop structure. By the way, in this lecture, I'm not trying to say the without loop solution is better than the other. This example is to just show how to solve this problem without the loop using the operator. Okay. To refer the location of the diagonal element, we need the logical matrix. Have a 0 except for diagonal element. It said 1. That is I matrix, but that is a numeric matrix. It's not a logical matrix. So if you convert this I identity matrix is a logical type, you will get this one logical. Okay. If you plug this in here, and then B is the B matrix is this one. B is here, and then you assign A to those location. That's why you will get this. Okay. How about assign this 8 in the reverse diagonal element? This is the key part. You can just flip in the left hand horizontal direction. If this one is a flip, you will get this indexing vector. So if you plug this in the C here, and then you will get this matrix. Okay? Can you get this point? So bottom line is, when you change the value in the matrix, okay, you first get the logical matrix, okay, that satisfies the condition that you're looking for. And then you can directly putting in this logical matrix in the index vector. That is called the logical indexing. So like this. You can plug in this logical matrix here. They're implicitly converted to the logical vector. Then this can help to easily change the value like this, because this one is referring those corresponding location. You can assign this, and then this example you can take advantage of the built-in function. Okay. Make sense? Please compare these two solutions. A few years ago, MATLAB started supporting comparable array sizes for operation. Do you think that this script is working? Based on the rule that we learned, it should not be working because it is element-wise operation, but the size of the elements are different. However, it is a working solution now. This operation is accomplished by this comparable array size support. For example, we already knew that this one is working. What is this operation? Is element-wise operation. This 2 is multiplied each element, right? So basically this operation is the same with this one. This scalar value is expanded to the same size of the array, and then do the element-wise multiplication. Okay, this comparable array size is similar. Okay, 2 inputs have the comparable size if for every dimension the dimension size of input are either the same or one of them is a 1. Okay. MATLAB implicitly expand the array with a comparable size to be the same during the execution of the element-wise operation or function. Okay, to understand this wording, let's take a look at this example. The every dimension is a row dimension and column dimension. What is the size? 3. What is the size? 2, right? And then this one is the row is the 3. And these are the same, right? That's why it's a comparable. What about the column? It's a 1. So here, one of them is the 1, right? That's why it's a comparable. Basically, this operation is can valid for supporting the comparable array size. Okay, so in this case, this vector is implicitly expanded to the same size of this one. How? This operation is to conduct this one. 2, 3, 1, 2, 3. Make sense? Let's see the more example. Many operators support this comparable size option. M1 and V1 are comparable size because I already mentioned that the row is the same, this columns, size is the 1. That's why, and every operation is like a plus, minus, and multiplication, a dot multiplication. This one is implicitly expanded to the 3 by 2 matrix. So by replicating this column to the second column. Make sense? What about this one? This one is 3 by 2. This one is 1 by 2. The second column dimensions are matched, but the row dimension, this one is 1. That's why it's a comparable array size. That's why this vector is expanded to the 3 by 2 by replicating each row to the second and third row. Make sense? That's why in here, basically, this operation is conducted this one. And when the V1 become like this. Okay, do this operation. What about this one? This one is a V2 become like this. Okay, so let's say this one is a V2 new. M1 plus V2 is the same with M1 plus V2 new. Make sense? What about the equality here? Equality is conducted on this one and this one. Okay, for this line, then this one and this one. Make sense? Okay. However, for matrix multiplication, this comparable array size option is not supported because this is the matrix multiplication. Inner dimension should be matched. For example, here there's a 3 by 2. This one is a 3 by 1, right? Inner dimension is not matched. That's why it's error. What about this one? 3 by 2 and 1 by 2. Inner dimension is not matched. So it's an error. So if you run this script, you will see these types of the runtime error. So I realized that many students unconsciously use this structure. Okay, for example, in here, this is here R is the R1, R2, R3, right? C is the C1, C2, C3, right? B is the B11, B12, B13, B22, B23, B2, B33. Okay. So let's take a look at the Math 4. Oh, no. Math 3. Math 3 is the that is, the answer is B times C, right? So this one is a C1, C2, C3, C1, C2, C3, C1, C2, C3, right? Okay, so you will get B11, C1, B12, C1, B13, C1, right? Like this. Okay, that is a model answer. However, in here, so let's resize to this one. In here, you can use the comparable size. How? Math 3, B, C. So why this one is working? This is a 3 by 3. This is a 3 by 1, right? This is a comparable size. So basically, if you do this operation, C is implicitly expanded to the, like this. That's why this one and this one are exactly same in MATLAB. Make sense? Okay. What about the Math 4? Math 4 is, the answer is, Math 4 is, the answer is, okay, Math 4 is the A times matrix multiplication A and B, and then plus C, right? Because it's element-wise the addition, right? In this case, you can simply plus a C. Why? A times B is a 3 by 3, C is a 3 by 1. This is the comparable size. Okay, that's why you can get Math 4. Okay. The tricky question is, I'm not sure the students already know this, comparable size support in MATLAB, but I'm not teaching this at the beginning because, students just make a lot of the mistake if they are not familiar with these types of operation. So initially they should match the size of the matrix or vector at the beginning, and then I encourage to use these comparable size the support options later. Okay, but the tricky case is Math 2. So Math 2 is, the answer is C times R. It's a matrix multiplication. So C is the, I write down this one, C2, C3, R1, R2, R3. This become a C1, R1, C1, R2, C1, R3, right? C2, R2, something like that, right? Okay. Here's the questions. What about this one? C is the 3 by 1, R is the 3 by 1, and R is the 1 by 3, right? So in this case, 3 and 1 is like a comparable size, right? This one is 1. 1, 3, this is also comparable size. So in this operation, C is explicitly converted to like this. R is explicitly converted to R1, R2, R3, R1, R2, R3, R3. Okay, and then do the element-wise operation. That's why this one and this one produce the same answer. Make sense? Here start the logical built-in function that is very useful and actively used to solve the problem in the rest of the course. These are the built-in functions that accept a logical array as an input. The operation is very simple. Any return true if at least one element in the input vector x is true. Here's the example. Any i2 is the false because there's no 1, right? And the i3, i4, and i1 is the true. Okay? Simple, right? On the other hand, all return true only if everything is true. That's why all i2, i3, i4 are false because there's a 0 here, but only the i1 give you the true. Make sense? What about the find? Find is the function to return the location of the true in the input argument. So here I1 is all this true. So one location is the first, second, third, and fourth, and fifth, right? That's why it gives you this one. What about the I3? The true location is second and fourth. That's why it's 2, 4. Okay, what about this one? And I1 and I3, that is the 0, 1, 0, 1, 0. Okay, and all that give you false because there is a 0. Okay, what about the and I3 and I4? That is 0, 1, 0, 0, 1, 0, right? And here, at least a 1 here, that's why it's a true. Okay, can you get this operation? This is a really powerful function that you will see the value. The previous question is to find the number in the input vector that satisfies this condition. Okay, we use this logical operator to generate the logical vector where the true location that satisfies the condition has a 1, a true, otherwise is a 0. Okay, that is how this works. Okay, I slightly changed this question. What if the question is asking if there is this number that satisfies this condition or not? Okay, we simply used any. Can you see the difference? For instance, here, if you try to find the number that satisfies this condition, you can simply, for instance, in the first case, and this one give you the number. In here, 10, 11, right? But this question is asking you, there is this number or not? Okay? But in this case, we can directly use this logical vector, and put this in any function. Okay? But any operation is at least a 1 here in the logical input vector, and that gives you the true, otherwise a false. That's why in this case a true, and then there's no 6, right, in this vector. That's why it's give you the false. What about this one, larger than 3 and less than 7? There is this number, right? That's why it's a true. As an optional discussion, how to replicate any function using the other built-in function. Okay, so here, how to replicate this line without using the any. Okay, one way is this one. Okay, imagine that some ID1 is summing up all this value. But basically, summing up the logical value means it implicitly convert it to the, the double and then adding up this value. That's why in this case, this one is the 2. 2 is larger than 0. That's why it's a true. In this case, there's no 1. That's why this become a 0. 0 is not larger than 0. That's why it's a false. Okay. Okay, let's revisit bulls and cow. How to compute the bulls plus cow using the logical operator. To solve these questions, previously we used the double loop structure to access each value in xtrue and xtest. Okay, so in this case we're comparing the individual number, right? But so rather than designing the double loop, we can solve this question using the single loop. How? We can use the operator. Okay, let's see this script. We just make the single loop, and then we are using this one. Okay, what is this one? We can read one test number and then do this operation between the vector and the scalar, and this give you the logical vector where the true if this number is placed in one of this element, that is 1, I mean true, otherwise 0. Okay, so if there is this number, this scripts give you the true. Can you get this script? Okay, if there's no this number, this logical vector is all 0. That's why any 0 gives you the false. That's why this one is the counting the num-c, which is the cow plus bull. Okay, make sense? So here's another example. Let's find out IDs of the students whose scores are more than and equal to 80 and less than the 90 in their midterm. This is a very good question to understand the operator. These are the two conditions. The score is more than or equal to 80 and the score is less than 90. The number should satisfy these two conditions. Okay. So when you look at this problem, you first find out the loop and then selection statement based solution. You have to know how to design the solution first. Okay, let's find out how to design those script. Okay, score and for I is equal to 1, 2, numeral, need the score, right? And what is the, okay, and then read the score, each score, need the score at II, then how to design the selection statement. Score is larger than or equal to 80 and score less than 90, right? And then do something. So what is the action that we are going to design? Assign the student ID, that is the CLID, class ID, initialize with empty vector, and then CLID like this. Okay, do you understand this solution? So if you run it, Let's do this. Okay. If you run it, the class ID is the 2378, right? Okay. Okay. Now we are going to figure out using the operator. We can use the relational operator between the vector and scalar. Okay. If you run the line here, what is the resulting value? This is condition 1. So if you want, the true location is the number is larger than or equal to 80 here. Otherwise, it's a 0. What about the condition 2? Condition 2 is the score is less than 90. Okay, so condition 2 is the here, right? These all the less than 90, but this is the more than 90, right? All 90. Okay, so to get the value between this 80 to 90, we can use the AND operator. Okay, this is the same thing with this operation. Only difference is this one is we are using the one single number. This one is we can play with vector. Okay, logical vector. So what is the IDX here? IDX is the logical vectors where each elements are true when both are true. So how to find out the location, the student ID? We can use the find function. Do you understand how to use this built-in function to get this value? This is the really nice solution rather than this one. I mean, both are the valid solution, but you know, you don't have to use the loop structure if you know how to use the operator. Okay. Okay, so here's the final example in this module. Let's solve this problem in the 3 different ways. Change 1 to 5, 2 to 7, and the rest to the 10 in the given vector, named the vec. First way is to use the selection and loop statement. Find the numbers of the element, that is n back, and then design the loop structure, and then evaluating each value to see if it is falls in this condition 1, 2 or rest 1, 2 and rest, and then assign the new value here. Make sense? The second method is to find the location where we can change the value using find. Okay, so what is this one? Find out the location of, assign the one in the location that satisfying this condition, right? So location 1, 2 indicate the location of the 1 and 2. Okay. How to find out the rest of the location? We can write this condition statement. Vector is not 1 and vector is not 2. Okay, can you get this logic? Now we are assigning the new value to here. Okay, what is the other indexing method? That is logical indexing. With this logical indexing, we can solve this problem without using find function. Okay? Because the reason I introduced this method is some students overuse this find function. But that's not wrong, but the solution without using find is much more simpler and readable. Okay, so I introduced in the third method. Okay, here we generate just the logical vector. This L1 location 1, 2 is just a logical vector. This is the rest of the location. How to find that? Location 1 and location 2 are logical vector where true is the location that satisfies this condition. Otherwise, it's false, right? So if you applied OR operator, that is the one location where this number 1 or the 2 are placed. Otherwise, it's 0, right? Make sense? So the rest of the location, just not this location. Then how to assign this value? You can simply using the logical vector to referring those location and assign the value like this. Okay, here you have to know the difference between these two. This one is here is the location. So this one subscript or linear indexing. This one is the logical vector. This is the logical indexing. Make sense? Okay. Personally, I recommend the third option. Okay, this one. But if you're not easy to implement the logical indexing, you can use this second script or even in the first script. Okay? This is the end of this module. From module 1 to 6, believe or not, you have learned most of the MATLAB programming. You are able to write a script for solving the actual problem. I understand that this class is going way too fast for some students to catch up. However, there's a trade-off. If you learn this topic later, you don't have enough time to do practice. From now on, we will solve the many different practice problems to improve your programming skill. The rest of the modules are more likely the syntax, such as the functions and new data types or the structure or the plotting. Thus, you can think that we will learn the new tool to just make our programming better and easier. Alright, and then see you next lecture. Bye.